I thought I'd talk about what is the virial temperature of a halo. And, you know, in a way, perhaps you know all this already. I'm not trying to insult your intelligence, but there's a lot of misconceptions that I see in literature about the idea of virial temperature. And I want to go through what I think about when I think about virial temperature, and hopefully it'll help some people fall into misconceptions less. So basic, you know, I'm sure you all know this, but one can write down an approximate virial theorem with similarity signs. The kinetic energy of a virialized system is supposed to be half the absolute value of the gravitational energy. And if we equate the kinetic energy with approximately the number of particles times kT, then you can say, well, kT is going to be roughly the circular velocity squared over 2 times the mean mass per particle, which is like the you know, gm over 2r. And so if you're just doing some estimates, that's often good enough. But when you want to do better, it's not good enough. Another thing is, in order to determine the virial temperature, you need to, someone's, yes, as I can see in the chat that a virus has crept into my title. I'll fix that later. But yes, autocorrect doesn't like the word virial. And now I see, right? So you have to, you know, you need to know mass and radius in order to theoretically calculate a virial temperature. And that gets us into the thorny topic of virial mass and radius. And so the reason it's thorny is the systems we're talking about don't actually have a good boundary. The mass trails off gradually with radius. And so in order to find virial mass or radius, we have to set some sort of arbitrary boundary. And what's most often done is it's set with respect to some overdensity. Sometimes it's an overdensity with respect to the critical density, sometimes it's overdensity with respect to the background density. And so there's a delta factor that says we're going to define the virial radius so that the mean mass density inside it is some multiple of, say, the critical density. And the delta is chosen to roughly divide the part that has kind of done gravitational relaxation from the part that's still infalling. The way, you know, if you do a little algebra, you can rearrange that definition to what I think is a convenient way of relating the circular velocity at a radius to the radius. And so the relationship, it's almost like a Hubble's law, sort of, for virial radius, where the ratio of circular velocity to radius is really a multiple of the Hubble constant at that time. And whatever that multiple is depends on what you chose for delta. So in a way, it's like saying the orbital time velocity over radius is like some of the age of the universe at a given radius, okay? But the problem, I think, is in literature, there's a whole lot of different tools that are used. There's too many definitions. There's a lot of justification for using each one, but it has complicated our task of trying to relate our works to one another because of this multiplicity of definitions. One thing of halos is, to lowest order, they have a constant circular velocity. So in that sense, the circular velocity of a halo is more definite than whatever we call mass or what we call virial radius, which means that the virial temperature is going to be more definite also. In a way, I like to think of halos more as having, you know, virial temperatures or circular velocities than you know, virial masses. Another thing is there's something sometimes called pseudo-evolution. The first time I learned this term was in a paper by Diemer, Moore, and Kravtsov, where if you just have a halo that's not evolving at all, it's just sitting there, the fact that you're measuring mass and radius with respect to some sort of multiple of the critical density means that halo mass and or virial mass and virial radius are changing with time, even though the halo is not changing at all. So that can be another point of confusion that comes in when you're trying to understand what the significance of virial mass and radius are. So I'm your cautionary tales there. But the real topic is virial temperature. So in the virial theorem for an isolated system, people are used to thinking of it something like this. The kinetic energy is 1/2 the magnitude of the gravitational energy, and then the kinetic energy is like 3/2 kT per particle. And that would give you a gravitational temperature that's like the gravitational energy divided by 3 times n particles. Okay, and that's okay for an isolated system with pure gravitational confinement, right? But there aren't isolated systems out there that we're talking about. If you actually have a boundary pressure, and this is if you go into the halo and you draw a radius and say inside of this is my virialized system, outside of it isn't, there's actually particles out there moving around which represent a pressure. And so you have to modify the virial theorem if you don't have a zero pressure boundary. And that leads to another term in this relation, a pressure term. And to know why can I just write that down? Well, you can look at that and say, well, what happens if I just send gravitational energy to 0? If I do that, what I obtain is nkt equals p times v. Okay, so if you have a boundary pressure, this way of writing down the virial relation can allow you to segue smoothly from a system that's mostly gravitationally confined to one that's mostly pressure confined. Okay, and so an example of this is if we just ask, what is a singular isothermal sphere like? A gravitational potential that has constant circular velocity. If you take a singular isothermal sphere and say, what's the gravitational energy once we draw a radius? That's mass times Vc squared. And then if you ask, well, what's the pressure out there, just what I associate with particle motions, it's 1/2 times the mass times Vc squared. And that means that the temperature of the system is the magnitude of the gravitational energy divided by 2n. Whereas, if now we've accounted for boundary pressure, what we think of as the virial temperature is actually 50% greater than the naive virial theorem. So don't forget that. Next thing, when we're talking about the gas part, the gas isn't self-gravitating. So we can use the virial theorem to say what are the particle motions like of the collisionless stuff. But actually, usually when we're talking virial temperature, we're talking about the gas, especially if we're talking about the gaseous halo. And in that case, it's best to start with the idea of hydrostatic equilibrium. And again, I like to rewrite the hydrostatic equilibrium equation. If I want to know the temperature, I can rewrite it in terms of the circular velocity and this logarithmic pressure gradient. And that means we can define something I think is gravitational temperature. In other words, if I have this relation as my expression of hydrostatic equilibrium, then if I define T sub phi, gravitational temperature, like this, then if my system is actually a singular isothermal sphere, then the hydrostatic equilibrium temperature is equal to T phi, all right? So the singular isothermal sphere is the closest parallel model we have to what cosmological halos are like. And so this expression in particular shows that what's really determining the temperature of gas in a gaseous halo is this gravitational temperature and whatever the pressure gradient is. So in order to change the temperature of the gas, fundamentally what I need to do is change the pressure gradient. It's independent of the absolute magnitude of pressure. What I'm actually doing is changing the slope somehow if I'm going to change the temperature. Okay, so what implications does it have? I pulled this figure out of a paper from Goulding et al. 2016, where they looked at Chandra archival data for galaxies in the massive sample, galaxies in the Atlas 3D sample. And so they had good velocity dispersion measurements of the central galaxy, and they're measuring the gas temperature in the central galaxy within the effective radius. Okay, and you can graph velocity dispersion and temperature, and then say, is the relationship? Well, obviously, gas temperature is well correlated with velocity dispersion. But if you kind of use a kind of naive virial argument, one way to capture the naive virial argument is something X-ray astronomers call beta spec. Beta spec is defined to be the mean mass per particle times the velocity dispersion, one-dimensional velocity dispersion squared divided by KT. And that can be rewritten as T phi over T. I put an approximately equal to here. It's an exactly equal to if this velocity dispersion is isotropic, but maybe the velocity dispersion is anisotropic a bit, in which case there'd be some sort of correction. But when you expect things to be like a singular isothermal sphere, then you expect beta spec to be 1, okay? And these magenta lines are the beta spec equals 1 lines. And you can see that, the relationship between velocity dispersion temperature has approximately the right slope, but it appears to be elevated in temperature, okay? And so this orange dotted line, I made it orange for the purpose of this figure, is up at beta spec of 0.6, which says the gas appears to be hotter than you expect from a simple virial argument, okay? And there's been a lot of, so this particular paper is looking at, how it depends on halo mass, how it depends on radio power, because, if the gas is hotter, maybe it was heated, okay? It also looks at, how much it depends on rotation. But really, the main thing that's going on here is it has a shallower pressure gradient. Something has happened to these systems to make the pressure gradient shallower. And if the pressure gradient is shallower, you're going to have a higher temperature for the given gravitational temperature. It's not a mystery. Some people even look at this and say, oh, this must be out of hydrostatic equilibrium because the gas isn't at the virial temperature. But all that's happened is there's been some heating process or cooling process, could be either, that has changed the pressure gradient. Okay, it's changed the mapping of gravitational temperature onto gas temperature. And so it's not a mystery. It's just how things behave when they're close to hydrostatic equilibrium. Okay, so what are the theoretical implications? First one, virial temperature it's a better way of thinking of halos than virial mass or virial radius because the problems I outlined in the beginning of the talk. Sometimes we do want to know mass, but there's a lot of ambiguities and contradictions in definitions of mass. Virial temperature isn't even really what you want to be talking about when you're talking about the gas, because virial temperature refers to a system that's self-gravitating. The gas is not gravitationally dominant, it's responding to a gravitational potential, okay? And when you move the gas around, the potential doesn't change, okay? So I prefer to talk about, is the gas at the gravitational temperature higher or lower? Then the question is, all right, I can calculate the gravitational potential of a halo, but if I want to know what the gas temperature is, the pressure gradient comes into play, and not the magnitude of the pressure gradient, it's just the slope. What does that mean? That means if I have a cooling flow that's operating and the pressure gradient stays the same, the temperature doesn't even have to change, okay? In a cooling flow and isothermal potential, the gas is being compressed as it's losing entropy and the temperature stays the same. So you can have a cooling flow and yet the temperature doesn't change, okay? It's mapping to the gravitational temperature. It also means that if you heat the gas gradually and it expands, but you haven't changed the pressure gradient, then it just expands without changing the temperature, okay? So I've ridden my hobby horse around a little bit to let you know what sometimes gets me going when I see some misconceptions in the literature. And I just wanted to do this tutorial. I think for the most part, I probably reminded you of things you already knew, but maybe don't always remember when you're trying to understand why gas has the temperature that it does in a gaseous halo. And so with that, I will stop sharing and head over to my breakout room if you want to talk about this further. I see there have been a lot of comments in the chat, but I'm going to head to the breakout room. Thank you for your time, and Cameron will be next.